Have you ever heard of a solid that's basically lighter than air? I'm talking about a material that looks like frozen smoke, but can somehow support thousands of times its own weight. We're talking about aerogels. And these seemingly magical materials are getting ready to completely change the game in medicine. So, what in the world is an aerogel? Okay, imagine you've got a block of jello. Now, what if you could pull out all of the water, every last drop, but without the whole thing collapsing into a puddle? What you'd have left? That's basically an aerogel. It's this incredibly delicate, solid network where all the liquid has been replaced by gas.
And that unique structure gives it some truly mind-bending properties. I mean, they can be up to 99.8% air, which makes them one of the lightest solid materials on the entire planet. They have this ridiculously high internal surface area. A piece the size of a sugar cube can have the surface area of a football field. And the most important part for medicine, we can now make them out of natural, body-friendly materials.
So, here's what we're going to cover. First, we'll get to know this solid smoke. Then, we'll check out the recipe for making it. After that, we'll dive into two of the most exciting medical uses, smarter drug delivery and building scaffolds for new tissue. And finally, we'll take a realistic look at the hurdles this tech still has to get over. All right, first up, let's get a closer look at this stuff. Its nickname, solid smoke, is just perfect, right? It captures that bizarre, almost ghost-like look. But don't let its appearance fool you. Its structure is its real superpower. Now this is where the magic really happens. We're looking at the nanoscale here, and you can see this huge, tangled network of pores. Think of it like a solid sponge, but with pores so incredibly tiny they can trap individual molecules. This is what gives it that massive surface area and what makes it so unbelievably light.
So how on earth do you make something that's mostly, well, nothing? The process is super delicate. It's a really cool bit of chemistry that turns a wet, wobbly gel into one of these amazing gas-filled solids.
The secret sauce is all in the drying. So first you make a wet gel, just like that jello we talked about. Next, you swap out the water for a solvent, like ethanol. And then comes the final and most critical step, supercritical drying. You use carbon dioxide that's been put under intense pressure and heat, and it gently lifts the ethanol out. This whole process avoids the crushing force of normal evaporation. It's like the liquid just sneaks out as a gas, leaving that delicate solid structure perfectly intact.
And you know, this process isn't just for silica anymore. The real game changer for medicine has been figuring out how to make aerogels from natural polysaccharides. You know, things like alginate from seaweed or cellulose from plants. This is huge because it means they're biocompatible, so your body won't reject them, and they're biodegradable, so they can just dissolve away safely when their job is done.
Okay, now let's look at how this incredible structure leads to our first major application, using aerogels as a kind of super sponge for delivering medicine in a much smarter way.
So here's a massive problem in medicine today. More than 40% of the drugs we have are basically like sand in water. They just don't dissolve very well. And if a drug doesn't dissolve, our bodies can't absorb it properly, which severely limits how effective it can be. This is a huge roadblock for a lot of life-saving treatments.
And this is where aerogels come in. Just look at the difference. In a normal pill, the drug is in a stable crystalline form, kind of like a sugar cube, so it dissolves slowly. But inside an aerogel, the drug gets trapped in a non-crystalline state. Those tiny nanopores keep the drug molecules separated so they can't clump together. The result? The drug dissolves almost instantly, which massively boosts its bioavailability. And that's just a fancy term for how much of the drug your body can actually use. And this graph shows you just how big a difference it makes. That flat line at the bottom, the one with the squares, that's the pure drug taken orally. It barely even registers in the bloodstream. But now look at the triangle line. That's the exact same drug just delivered in an aerogel. It's a total night and day difference. Not only does it reach a much higher concentration, but it stays in your system for way longer, giving a steady, lasting effect. But wait, it gets even better. Scientists can actually fine-tune how quickly the drug is released. By using different natural materials, like pectin or alginate, they can create a formulation that gives you a quick, fast-acting burst or one that gives a slow, steady release over a long period. This versatility makes aerogels an incredibly flexible platform for just about any kind of therapy you can imagine.
So delivering drugs is one thing, but the next frontier sounds like it's straight out of science fiction. We're talking about using aerogels as scaffolds to literally rebuild parts of the human body.
The idea behind it is actually pretty simple, and it's brilliant. You implant a porous aerogel scaffold right where new tissue needs to grow.
let's say to repair a piece of bone. Your body's own cells then move into that scaffold using its interconnected structure as a template to grow on. And as your new healthy tissue forms, the biodegradable aerogel just dissolves away, leaving nothing behind but you.
And these polysaccharide aerogels are just perfect for the job. They're made from abundant natural stuff, they're non-toxic, they dissolve safely, and that porous structure is exactly what cells need to attach and grow. On top of all that, some of them are even strong enough to support the regeneration of bone, which is incredible.
And hey, don't just take my word for it. This quote from the journal Advanced Materials Letters points out that cellulose derivatives, so aerogels made from plants, are getting a lot of attention for their outstanding mechanical properties, making them a top contender for these really demanding tissue-building jobs.
Okay, as amazing as all of this sounds, this technology isn't exactly on the shelf at your local pharmacy just yet. It's really important to take a clear-eyed look at the real-world hurdles that researchers are working hard to solve right now.
So what's the catch, right? I mean, why aren't we all taking aerogel pills and growing new bones today? Well, there are a few key challenges.
For one, there's structural stability. Some of these biodegradable aerogels tend to collapse when they get wet inside the body, which can mess with their performance. Then there's the issue of scale-up. That super precise, multi-step recipe is really complex and expensive to do on a massive industrial scale. And finally, it's actually really hard for scientists to see what's happening to the drug when it's tucked away inside those impossibly tiny pores.
But there is some really good news on the horizon. Research into scaling up production is already showing some huge promise. One study found that just by moving from a small lab setup to a larger pilot-scale plant, they could potentially slash the environmental impact of the whole process by over 70%. So as it gets bigger, it also gets cleaner and more efficient.
Which brings us to the big question at the end of all this. Aerogels give us a toolkit that sounds like pure science fiction. We're talking about materials that can make powerful drugs effective, release them on a perfect schedule, and even give our bodies a framework to heal themselves. So, with the power to rebuild our bodies and deliver medicine with pinpoint precision, are we on the verge of the aerogel age?